Hey class, Mr. Moyton here. Sorry I can't be with you in class today, but I figure I'll use this video to help you out with a topic that, from my observations, tends to be a challenging one, especially at the start of a unit like we're in right now, and that's figuring out which of the four criteria a given picture may illustrate. So if you take a look at the handout that you were just given, I have the same copy here. It says, which criteria, if any, can be used to show the triangle is congruent, and if congruent, complete the congruent statement. So that's one of these things here, where the order matters. So if you recall, the four rules we're allowed to use are side, 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 angle, angle, and angle, angle, side. So if our triangles meet those criteria, then they're congruent. If not, then we do not necessarily know if they are congruent, even if they look like they might be. So let's take a look at this first example here. You see that there are two pairs of angles given, the double striped and the single striped. And that's it. There's only two pairs of angles. So right away, you know that the answer, if it's any, is going to be one of these two. Why? Because they both have two pairs of angles in their acronyms, right? Angle, side, angle, 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 side. And there's an angle right here, and there's an angle right there in the top triangle, right? Well, they have no side information given, and that's a bummer. However, as you saw from the computer lab the other day, and also just from simple observations, you see that they share this side right here, right? Both triangles, if you were to separate them, if you were to sort of, split them apart, you would see that they both share side length BC as one of their sides. So it's congruent to itself, and if you recall, that's called the reflexive property. So we're allowed to mark that because shared sides are congruent because they literally have the same length in both shapes. It's the bottom part of the top triangle, it's the top part of the bottom triangle, so to speak. So really we have three pieces of information, the two angles that are given, and also a pair of sides that happen to overlap. And in a way, you can see what the answer is right there. You've got a pair of angles on either side, and in between them, physically, right, is a side length connecting them. So the rule that we're looking at here is angle, side, angle. Now, people often confuse angle, side, angle, and angle, angle, side, so keep this picture in mind when we look at a contrasting picture in just a moment. So since they are congruent, we're supposed to write a congruent statement where order matters. So if we take a look here, we have angle A, and then B, and then C. So the name goes in this manner right here. The unmarked angle to the single marked to the double, right? So the order here would be unmarked to single to double. So that would be D, C, B. So DBC would not be right. DCB matches the order here. Let's take a look at number 2. We're given this information. Let me do it given in red just for consistency's sake. We're given this pair of angles, and we're also given this pair of sides. So let me mark those. We have a pair of angles here and there, and we also have a pair of sides in each shape. Okay? Well, and that's it. That's all we're given. But if you recall from the computer lab, and also just from, hopefully by practice now, you'll notice that we have, not as an assumption, but something we've already proven, that these angles here, which are vertical angles, we've already proven, one of our very first proofs, that those are congruent. So we know, even though they're not given, that they are indeed the exact same measurement. So that's a pair of angles that we can logically deduce. Now you might think, well, okay, this appears to be ASA as well. But look carefully at the way the shape is oriented. You have these two angles, here in red and here in blue, right? In between them is this side length here. That's literally connecting the red to the blue. Is that the marked side? Well, I don't see any mark here. And likewise, between the blue and red angle over there is no mark between them either. So ASA is not a good description for what we're looking at here. This says an angle, a side, and then an angle. Or a side with two angles on either side of it. And that's not what we're looking at. So instead we have two angles, and then a side not in between them. So this is an example of angle, angle, side. Angle, angle, side. So once again, we have to give the order of the name here. Well, let's see. It starts off as JGH. The middle, double striped to the blank to the single striped, JGH. So double striped is J here as well. Over to G is the blank one. That's W in this case. JGH, JWY. Alrighty. Let's look at a couple more. All right, so what are we given here? We're given some side information. That pair of sides congruent. This pair of sides congruent. And that's all we're given. We're given no angles at all. Right? No little stripes in the corners of any of the vertices there. So that's a bummer. Well, if there's no angles given, then it appears if there's no vertical angles, because we don't seem to have this configuration here, then our only choice might be side, 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 because that's the only one that doesn't have any angles involved, right? But we're missing a third pair of sides until you realize that just like in this problem up here, you have this shared side that both shapes literally overlap. They share that side. SR is the same length as itself, and that's an idea called a reflexive property. So a pair of sides match, a pair of sides match, those are given. A pair of sides is sort of hidden because it's on top of itself, so we have indeed three pairs of sides. They are indeed congruent by SSS. So this one is called E to R to S, ERS. Well, E is where 2 meets 3 here. So 2 meets 3 would be H. E to R is traveling along this little 3 marked one, and then over to S, so that would be H to S to R. HSR. Looking at the fourth example here, well, let's take a look at what we're given. We're given quite a bit of angle stripes, so one there, one there, one there, and then correspondingly over here as well. And we're not given any sides at all. And if you look back at the shortcuts here, based on what we found in the computer lab, every single set of triangle congruence requires some sort of fixed length, some sort of side length congruence. And we don't have any, right? So all we're looking at here is an example of angle, 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 which is not really a rule. It's not one of our 4 criteria for guaranteeing the same shape. So these are not necessarily congruent. And you can kind of imagine that if, there's no way to know if these are the same size just because they have the same angles. Imagine shrinking one of these shapes a little bit, right? It could be the exact same shape with a different size, and that means they're not identical. They're not congruent if they differ in size. So this would be an answer of none. And since they're not congruent, there's no need to write a congruent statement because that would be false anyway. Looking at the last 2 here, once again we're given one pair of sides and a second pair of sides. So 2 pairs of sides, and we're also given that this angle is 90 degrees. But frankly, it doesn't have to be 90, because as we've already established, vertical angles are always congruent. So whatever this happens to be, even if we're unmarked, we know that must also be the same length. So what do we have? We've got a pair of sides, another pair of sides, and where they meet, or between them, connecting them, you have a marked angle. So 2 pairs of sides, and in between them a marked angle. Well, this is an example of what's called side, angle, side. Right, once again, if you label it, it kind of shows you the way this works. You got the side that's given, you got this angle, which is from vertical angles, and this pair of sides. They're all sort of grouped together here in this order as you go around the shape. Side, angle, side, congruence. So let's give it a proper name. It's called ACV. It's kind of hard to see in my version here, but it starts at A, goes to C, the middle here, and then over to V. It looks like A is the same length, size as R. And you travel along the 3 tick mark all the way up to the 2, so that would be RCJ. And finally, our last example here, we're given these angles, one pair there, and a second pair there. No sides given at all. Well, we saw that earlier, didn't we? Well, it looks like it would be an assumption, so let me show you an example of what you don't want to do. It would be an assumption to say these are the same length. We don't know that. They don't overlap. They're not marked. We have no idea how long they are. Likewise for these 2. However, QL is the same as QL because both shapes share it as one of their sides. So it's the same as itself. Right? So you have a pair of angles, the ones that are given, and you also have, quote-unquote, a pair of sides that's sort of, you can't see one of them because it's underneath the other one. So you have 2 angles and a side, which again could be either one of these. But if you look at the orientation, in between the 2 angles, you have a marked side. Right? Literally in between them. If I cover one of them up, or if I just draw this separately here, this shape over here would look like this. An angle, another angle, and in between them is this shared side length. So this is an example of angle, side, angle again. So let's give it a name to close out. Q to U to L. Q is single stripe to blank to double. That would be LTQ. LT. Alrighty, hope this gives you a better feel for how to recognize triangle congruence.